In this worked example, I'm going to show how you can use the brightness of something, a standard candle, something which you think is always the same, to work out distances. Now let's imagine there's some nearby galaxy, and you know how far this one is. You know this one is 5 megaparsecs away. You point your telescope at it, and you find the brightest star in this galaxy, and you measure the flux from that. The flux from the brightest star in this galaxy you measure as 2.1 by 10 to the minus 17 watts per meter squared. Remember that flux is the amount of energy received in your telescope divided by the surface area of your telescope. So, you know how far away that galaxy is, but let's say you've now found another galaxy. Let's say it looks smaller, so you imagine it might be further away, but you don't really know. And you also find the brightest star there. For this brightest star, you measure a flux of only 4.7 by 10 to the minus 20 watts per meter squared. Much fainter. So that presumably indicates that galaxy 1 is closer than galaxy 2. But how far away is galaxy 2? Well, to work this out, we'll need the inverse square law. This tells us that the flux received from some object is equal to its luminosity divided by 4 pi and the distance squared. Now we're going to assume that these brighter stars are standard candles. They all have the same brightness, the same assumption that Edwin Hubble made. Not a good assumption at all, but let's go with it. In that case, we know that for flux from the brightest star in galaxy 1 is equal to the luminosity divided by that, and for galaxy 2, flux of galaxy 2 equals the same luminosity, because we're assuming they're all the same, over 4 pi distance 2 squared. Divide these two equations by each other, and you end up with f1 over f2 equals L over 4 pi d1 squared all over L over 4 pi d2 squared. Luminosities cancel, 4 pi's cancel. So that just comes out as d2 over d1 all squared. Now what we know is this, and what we want to know is that. So let's take the square root of both sides of this equation and rearrange, and we find that d2 is equal to d1 times the square root f1 over f2. Plug in numbers, and we find this comes out to a whopping 106 megaparsecs. So if our assumption is valid, and the brightest stars here really have the same luminosities as the brightest stars there, then D2 is 106 megaparsecs away.